Hi, this video is an introduction to chemical equilibria. The first thing I'll talk about is the equilibrium constant in general. Now, your equilibrium constant is set up as a large K, so you're going to say a big K a lot of times. And if you have a reaction such as this very simple one, A plus B equals C plus D goes to, you're going to have products over reactants. And everything is going to be taken as a concentration in brackets. So the big A, B, C, and D are the chemical species that have certain concentrations. And what they're going to do is you have the coefficients, right? So 1, 2, 3, etc. Those coefficients become the exponents in your equilibrium constant equation. So you have the large K equals the products. Those are all multiplied times each other, raised to the power of their coefficient, divided by the reactants multiplied together, and raised to the power of their coefficient. The thing that's important here is that you need to use everything in standard states. And so for liquids, that means the solute concentration is in molarity, moles per liter. Gas concentrations will be pressure in bars. And you're going to leave out any pure solids, liquids, or solvents. Their concentration will essentially be 1. And so if it's an aqueous solution, it's just water, leave water out of it. Furthermore, if the K value is much greater than 1, or actually just greater than 1, the forward reaction will be favored. And so that means that your products are greater than your reactants. If you have a K of greater than 1, therefore more products equals more forward reaction. Now, to manipulate equilibrium constants, you first have to realize that if you reverse the direction, then you're basically flipping your numerator and denominator in the equilibrium constant. And so if our forward reaction is this, HA goes to H plus A minus, and your equilibrium constant has the H plus and the A minus on top, as soon as you do the reverse reaction, you flip those around, then of course those things that were products become reactants. They go from the top to the bottom. So it's 1 divided by the number if you happen to have a number for that equilibrium constant. The other thing is that if you're you're adding reactions, then the equilibrium constant is going to be a multiplication of these. So we have an example here of K1, K2, right? And so these are equilibrium constants for these first 2 reactions. You see one is that HA going to H plus A minus. And then you also have that H plus could go on and react with compound C, and that can create CH plus. And so if you add those 2 things together, because the H pluses are canceling out, then you have to multiply the new K values together. Okay, for the autoprotolysis of water, what you need to understand here is that water will undergo self-ionization. So just neutral water will react with itself. One water molecule will take a proton from the other one, and it leaves behind H3O+, which we usually cheap out on, and we just call it H+, although there's never H+ alone in an aqueous solution, and OH-. So you've got the acidic and basic components of water just as it automatically loses a proton or gains a proton. And this has its own special equilibrium constant, still a large K for equilibrium constant, but it's got a W for, you guessed it, water. And it's Kw equals concentration of H plus times the concentration of OH minus, because those are the 2 products. It's not divided by the concentration of water because water is your solvent, pure liquid, so to speak, and so it doesn't feature in the equilibrium constant. At 25 degrees Celsius, Kw is equal to 1.01 times 10 to the minus 14, and it happens to change with temperature. And because it changes with temperature, you will be able to calculate that the pH also changes with temperature because the amount of H plus present changes. So equilibrium with respect to thermodynamics. First, a review of some thermodynamic terms. Enthalpy, if we have the change in enthalpy or delta H, this is the heat absorbed or released, and it's assuming constant pressure. What you need to know about this is negative delta H is an exothermic heat releasing reaction, and positive delta H is endothermic heat absorbing reaction. Standard enthalpy refers to things in those standard states. So I just mentioned standard states as molarity for solutes, it's pressure in bars for gases, that kind of thing. And that's usually what's tabulated. So if you go and you look up the enthalpy tables, you're going to see something like this, where you have the change in enthalpy with a little circle, and that little circle is saying standard. Entropy, abbreviated as, is a measure of the disorder of things. A classic and stupid joke is that you have a high entropy room when you're not trying to clean your room. Most parents don't believe in the entropy of the universe always increasing, and they want you to put some work in. Anyway, so entropy is a matter of disorder. Gases are more disordered than liquids. Liquids are more disordered than solids. And if you have something that's dissolving from solid into liquid, like a salt dissolving, then you're going to have a larger positive entropy because you do now have more molecules moving around. Gibbs free energy puts these together, and so Gibbs free energy is delta G, and it describes whether a reaction is favorable or not, and that considers both the enthalpy and entropy considerations. So delta G, Gibbs free energy, equals delta H, enthalpy minus T, temperature in Kelvin, times delta S, the change in entropy. A reaction is favored in the forward direction. It will be spontaneous in the forward direction if you have a negative delta G. With respect to the equilibrium constant, because I just talked about favored in the forward direction, the equilibrium constant K is related to delta G by this equation. So delta G equals negative RT natural log of K. And you can rearrange that to isolate K on its own by undoing the natural log, by putting everything else with the delta G and taking it to an e to the minus that power, right? And so what's going on here? Well, T again is temperature in Kelvin, R is our gas constant, and the more negative your delta G is, the larger positive K you have, so spontaneous. We know that makes sense because more of the concentration of products means that it went forward into that right-hand side of the reaction. Le Chatelier's principle, most of you who've done general chemistry will remember this. It's saying that if you disturb a system that is at equilibrium, it will try to return to equilibrium by offsetting the change. So if you take away a product, it'll try to move towards the products to fill that in. If you add a reactant, it'll move away from the reactants to get rid of that. If your reaction includes heat in some way, you have to think about where that goes. Exothermic reactions, we consider heat to be a product on the right-hand side. For endothermic reactions, heat is considered to be a reactant, so it's on the left-hand side. To figure out mathematically what way a system will go in order to reach equilibrium, what you do is you set up a reaction quotient, which is big Q for quotient. And you do this the same way you're going to set up the equilibrium constant. So here's a nice, beautiful, complicated looking ionic equation. We've got bromate plus chromium plus water in equilibrium with bromine, dichromate, and some protons. So for K, for the equilibrium constant, you're going to set that up. You've got all those products times each other raised to their powers. The H plus is the only thing with a coefficient, and so it gets raised to that 8th power because there's 8 H pluses. The reactants go in the bottom. There's no water there because, again, water is a pure liquid. And so we've got this essential setup for K. Now, if you want to know is something at equilibrium, you will take a look at the concentrations. So here's some concentrations for you. And you're going to plug those concentrations where they go in for K. But because we don't know it's at equilibrium, we're going to call it Q for reaction quotient. And once we plug those in their respective locations and calculate it out, you're going to get a number for Q. And in this particular case, the number for Q is bigger than K. So Q ended up being 2 times 10 to the 11. K is just 1 times 10 to the 11. And since it's bigger, it means there are excess products. And so if you have a Q that's bigger than K, because you have excess products, larger number on top, the reaction is going to shift leftward towards the reactants. So that's how we go about doing this mathematically for Le Chatelier's principle. Now, acid-base equilibria. One of the first things to remember is the definition of acid or base. Protic acid and base chemistry really is referring to the transfer of proton, H+. So acids are considered to increase proton concentration in aqueous chemistry, and so remember protons are also H3O+ because they're stuck to water molecules, and bases will decrease the H3O+ concentration in aqueous chemistry. The Bronsted-Lowry definition is that an acid is a proton donor, so it'll give up that proton, and bases are proton acceptors. And it doesn't really require an H3O+ molecule around, it just requires protons to be exchanged. And so it applies to more solvents, non-aqueous solvents, and to gases. Furthermore, there's the Lewis definition of acid and base, where we're talking about electrons. And so since electrons are negatively charged, protons are positively charged, the Lewis definitions are backwards. From Bronsted-Lowry, so Bronsted-Lowry says an acid is a proton donor. Lewis' definition said acids are electron acceptors. And so you want to keep in mind what these different meanings of acid and base chemistry are. Now, conjugate acid and base pairs are a huge concept in analytical chemistry and in equilibrium, because acids will donate protons to bases, and acids that differ from a base by just this one proton are considered to be an acid-base pair. So here in blue, you have acetic acid on the left-hand side, the blue labeled acid, and it will give up a proton and it suddenly then becomes the acetate ion, okay? The acetate ion in reverse could grab a proton from something and become acetic acid. So these are an acid-base conjugate pair. Methylamine here on the left-hand side in black and white is the base. When it takes the proton from acetic acid, the methylamine becomes its conjugate acid of methylammonium ion. So they have to be the same molecule, only differing by one proton. Now, I've mentioned already what Kw is, the equilibrium constant for water, and you probably know what pH is, but just a refresher, pH is the negative log of the hydrogen ion concentration. pOH is the negative log of the hydroxide ion concentration, OH minus. Because water is autoprotolysing itself to create H plus and OH minus, and because Kw is a constant, right, at any given temperature anyway, and equals the concentration of these two things, what you could do is you could do a negative log of everything in this Kw equation. And so we can have P of H, right, so negative log of H plus, and P of OH, negative log of OH minus, and that would equal the negative log of Kw. And the negative log of the 1 times 10 to the minus 14 happens to be 14. So the magic here is that pH plus pOH equals 14 when we're at 25C. So, strength of acids and bases. If you have what we call a strong acid or base, that means that this acid or base completely dissociates in solution and the K equilibrium constant is just huge. It's so big we don't even put a number on it because there's really no completely associated acid or base left. Weak acids and bases only partly dissociate, and so we have an equilibrium constant for acid, Ka, and we have an equilibrium constant for base, Kb, which are small. For weak acids, here's the formula. So HA to H plus and A minus being the conjugate base of the HA weak acid. A here is just being used as a term for any acid. And Ka is those products over the reactant. For bases, sometimes people will write this as A minus as the base. Other times they'll write it as B. Pick and choose whatever suits you. With the base though, it's a reaction between the base and the water. And the water is going to give up its proton to the base, making the conjugate weak acid BH plus and leaving behind OH minus. And your Kb is the BH plus concentration times OH minus concentration over B. Again, water doesn't feature because it's a pure solvent. All right, so we have our definition of Ka and Kb. I really want you to understand these equations and understand that weak acids are just giving up their protons some of the time, and weak bases are taking a proton from water. We're all talking about aqueous chemistry. You should memorize the table of strong acids and bases, and then pretty much everything else that's an acid or base is weak. Note that HF, although fluorine is a halogen, is not a strong acid. HF is actually pretty stable as a molecule. So weak acids and bases. Other than memorizing the strong ones and looking for things that are not in that list, a common class of weak acids are carboxylic acids. So this is our organic acids with our C double bond O, OH, and they can lose that proton on the OH to become their counterion. And so here you have acetic acid becoming acetate, and we have a Ka value for how likely that is. Common weak bases are amines, such as methylamine here. That nitrogen with that lone pair of electrons is happy to take on another proton and get a positive charge in the nitrogen. Now, strength of these, we can basically take a p-value of anything. So if pH is negative log of H, pKa is negative log of Ka, pKb is negative log of Kb. If the acid dissociates more, and so it's a stronger acid, Ka, just plain old constant for that is large, and the negative log of this large Ka is going to be a smaller pK. So small pKa means strong acid, large Ka means strong acid. Same concept for base. If the base is going to be more likely to abstract that proton off of water, it's a stronger base, producing more OH minuses left behind. Then you have a large Kb and a smaller pKb. The relationship between Ka and Kb is such that if you have things in water, Ka times Kb equals Kw. Now, how does this come to be? I've written for you here the weak acid and weak base equations. And so weak acid, you have Ha going to H plus and A minus. For the base, I've chosen to write the base as A minus, taking the point of view of this conjugate base and its interaction with water. And if I add these two reactions together as they're written, what you'll see is that we can get the equation for the autoprotolysis of water, because the HA cancels out on both sides. So it's a product and a reactant. When you're adding it, then it goes away. And the A minus does the same. So what you're left with here is H2O on the left side, and you have H plus and OH minus on the right side. And so if you write that out, then you've got the autoprotolysis of water. And we know from manipulating equilibrium constants that what you're going to do if you're adding equations is multiply the equilibrium constant expressions. And so we take all of the stuff on top, divided by all of the stuff on bottom, and you get this big mess for Kw, but it's actually not that messy because, again, the Ha and A minus on top will cancel out with the ones on the bottom. And so you're left with Kw equals H plus times OH minus. It's like, oh, okay, sweet. Because I added these reactions, the Ka and Kb reactions, if I add them together, I'm adding them together and multiplying their equilibrium constants, so Ka times Kb, and that happens to give me the same thing as Kw. So that's pretty cool. This means that if you have the Ka for something, then you're able to calculate the Kb. So in this case, we have the Ka for acetic acid, 1.75 times 10 to the minus 5, and we're going to solve for Kb. We take Kb, we isolate it, so we take Kw over Ka. We plug in our known numbers for Kw and Ka, and we're able to calculate the Kb. There are also polyprotic acids and bases that are compounds that can donate or accept more than one proton, thus the poly part. So oxalic acid is a diprotic acid. It can donate 2 protons, and so it has 2 Kas. The blue protons here are the ones being lost, and so you see in the top left that oxalic acid has 2 H's. And after it loses the first one, it's created an intermediate compound, the monohydrogen oxalate, and it has a certain Ka. Then that compound can lose its other proton in a second equilibrium expression and become the fully basic form of oxalate. Furthermore, there are polyprotic acids and bases that are tribasic or triacidic or even more than 3. Phosphate is a really common tribasic compound. So in the first step there, it's taken that proton from water. In the second step, it's taken another proton from water. And in the third step, it's taking another proton. And so we have the phosphoric acid as the fully acidic form of this, and we have the phosphate as the fully basic form. And it's a 3-proton step between each of them. Each step has its own Kb. And if you wanted to look at it the other way, of phosphoric acid losing its protons, you could also calculate the Kas. Now, because of polyprotic, it's the neighboring pairs that we look at. So we still have this concept of Kw equals Ka times Kb, but you have to keep track now of which ones we're talking about. So the Ka1 is the one going between, say, H2A and HA minus. And that's like for a diprotic acid on the left in the middle of the page here. And that is conjugate to Kb2. So that's your last abstraction of water. So Ka1 times Kb2 equals Kw if it's diprotic. Basically, you're going to go crisscross. So if you've got the A1s and B1s and stuff like that, you're going diagonal between A1, B2. If it's triprotic, it's A1, B3, A3, B1, and then A2, B2. And the Kas and Kbs are numbered. Ladder diagrams are a really helpful thing to think about what your main species is, particularly if you have polyprotic acids and bases. To make a ladder diagram, you first get the pKa values. So here's our oxalic acid, diprotic acid. And we calculate the pKa values by taking the negative log of these Ka values. So here and here. And you see what I mentioned earlier, which is the bigger Ka1, so 10 to the minus 2 is a larger number than 10 to the minus 5. So that larger Ka1 ends up giving us the smaller, more acidic pKa. Next, what you're going to do is you're going to draw lines for as many pKa's as you have, and underneath those lines, you're going to label them with pKa values. Now, this is a pH scale, and so the pKa value is saying a particular thing about what dominant species you have. And so for pKa1 of 1.27, it's really telling us that that's the concentration where you have equal oxalic acid and monohydrogen oxalate concentrations. If your pH is less than that, say your pH is 1 or 0.5, your dominant form of this acid-base pair group is the fully protonated acidic form oxalic acid. If you happen to be at a pH of 3, then you have formed monohydrogen oxalate, and that's the main compound present. And if you're at a pH that's even more basic than pKa2, so you're out at, say, a pH of 6 or something like that, anything above 4.27, then most of it is present in the form of oxalate, the fully basic form. At the particular pKa numbers, this is telling you you have equal concentrations of the two forms of the acid or base that are right there. So because Ka1 of 1. That gives you pKa of 1.27 is the oxalic acid and monohydrogen oxalate, H2A and HA-, those are the two species that have equal concentrations right at a pH of 1.27. Same thing for the other pKa. Okay, now the last basic equilibrium thing here is solubility product. And here we're talking about solids that are dissolving into solution. The solubility product, again, is an equilibrium constant, but it's particularly for reactions where you have a solid salt dissolving into its constituent ions. So, for example, we have mercury 1 chloride dissolving in water. And so it's mercury 2, chloride 2 solid in equilibrium with mercury 2, 2+. Now remember, mercury is a weird ion. And so it's not mercury alone, it's mercury 2, 2+, plus 2 chlorides. The KSP equation for this is, again, products multiplied by each other and raised to their coefficients as the powers. So there's no coefficient for the mercury 2, 2+. It has no power around its brackets, but there's 2 chlorides. So it's the chloride concentration squared. Now remember, solids don't feature in any kind of equilibrium constants, and so the solid mercury chloride does not go on the bottom, it does not appear. And now when this was measured, it's 1.2 times 10 to the minus 18, so cool. What this is telling us, though, is that you have to have this excess undissolved solid. Like, there has to still be a mercury chloride solid in there in order to be at equilibrium. If there's no solid left, it's not really at equilibrium, and so be careful about these kinds of things. Those KSP constants are available in the appendix of pretty much any analytical chemistry textbook and Gen Chem book. The last thing is the common ion effect, which is a special case of Le Chatelier's principle, and it applies in the context usually of these solubility product things. And what you want to think about is we have this equilibrium for that mercury chloride. What happens if we add sodium chloride? So the mercury chloride reaction was here and its KSP is there. Now the sodium chloride is going to create sodium plus, which doesn't really do much because it's not part of this reaction. But it also forms chloride minus, and chloride minus is a common ion. It's in common with mercury chloride in that it's on the right-hand side of the solubility product. And so if you're increasing your products, then you have to shift to the left. And so it's going to cause more mercury chloride to precipitate out because the mercury chloride is the solid on the reactant side of this. So again, it's just simple old common ion effect. We increase the chlorides. Chlorides are on the right-hand side as the product. It's going to shift to the left away from that to reduce the effect of it. Okay, that's your intro to equilibrium chemistry, and I hope that you learned a lot. Bye now.